Hi everyone, it's Wednesday, which means it's time for the Chem Help ASAP live stream. I think my mic is a little bit hot here. OG benchmarks, help me out. Tell me if my mic's a little bit hot. Audio's good. All right, good. It looked like I was kind of getting into the red there. Okay, so today we are doing some more acids and bases. So last week we worked with buffers. This week I thought we would do a titration. Now I'm giving it a little bit of a twist because we're going to do a titration of a weak base with a strong acid. So usually when you do titration problems, very often you'll do a weak acid with a strong base. But if you're pointing towards like your exam, if you're taking Gen Chem in college, or if you're pointing to, say, the AP exam, they love adding these little twists in that it's similar but not exactly the same. So I thought I would do the same thing in the live stream. As always, if you've got questions, please post them in the comments. I'll keep an eye on what's going on over there. And whatever you're working on in class that you need help with, or again, because we're getting close to the exam season, if you're studying and you know you need help on a specific topic, please let me know. You can email me. You can leave a comment in the chat today. You can also just leave a comment later on in the live stream if you're watching later. You can also contact me via Facebook. So you can leave a comment or direct message me on Facebook as well. So we try to hit all of the different outlets for contact. Okay, with that being said, let's go ahead and jump into our titration problem. All right, so I'll just read it. It's got obviously different parts to it. So we've got a 25 milliliter sample of 0.1 molar pyridine. We give the KB for that, and it's titrated with 0.1 molar nitric acid, which is a strong acid. So we want to calculate the pH of the solution in 4 different scenarios. So first, in part A, we're going to calculate the pH of the solution before any acid has been added. Then in part B, we're going to calculate the pH when 15 milliliters of acid has been added. In part C, we're going to go when 25 milliliters of acid has been added. And in part D, we're going 35 milliliters of acid. So what we're going to do is we're going to hit the pH before we add any acid, before the equivalence point, at the equivalence point, and after the equivalence point. Now, one thing I like to do with these problems is just do a quick calculation to know where the equivalence point is. Now, this one is really easy because my concentrations are the same. This is a 1-to-1 ratio. So that means my equivalence point is going to be at 25 milliliters of acid added. So you can see this is part C. If you can do that, especially if it's a quick calculation, then when you go to do your stoichiometry and you go to do your limiting reagent, then you already know ahead of time what the limiting reagent is, right? So at the equivalence point, it means you have the same moles of base and acid. So if you're before the equivalence point, then your acid is your limiting reagent. You haven't added enough yet. And once you're after your equivalence point, then your base is your limiting reagent and your acid is in excess. So for me, I always like to get that equivalence point in, and it helps me predict where I'm going to be either before the equivalence point or after the equivalence point. Okay, so let's go ahead and jump into our calculations here. Of course, we'll start with part A, and we'll just work through all of our acid base different parts. So we'll do for at least for A, we're just dealing with equilibrium. Now, pyridine, I should say, okay, so pyridine, I don't want to write that here because that's where my face is. All right, pyridine looks like this. OG benchmarks, bear with me. I know I am not as neat a drawer on organic structures as you are, but this is what pyridine looks like. I don't want to be drawing the structure or doing the molecular formula. So I am just going to call pyridine B for base in my chemical equations. This is just going to simplify things for me. Again, if you're on an exam, you want to make things really, really simple. Always do these. You can do acids as HA, and that's a very common thing to do. So I'm just going to go ahead and call pyridine. It's a base. I'm going to call it B. So again, we're doing part A. So we have no acid added. We just have pyridine in solution. So we have our pyridine, which is our base. I'm calling B. And of course, we're in aqueous solution here. I'm not going to deal with an acid or a base that's not in aqueous solution. It gets protonated, and then of course you have hydroxide left over. So the water is acting as the acid, it's donating the proton. Okay, so again, this is in equilibrium. here. You can see I drew my 2 arrows. So all we've got is just a really simple, straightforward equilibrium problem. I'm going to set up an ice table. Okay, so my I is my initial concentration. Well, that's coming from my problem. So that's very easy. I have a 0.1 molar. I don't need to worry about water. I have no protonated base or hydroxide at first. Then I have C, my change or my consumed, however you want to think about it. Again, we know the equilibrium is going to shift to the right because right now we have no products. So that's how we get our minus X on the reactant side and our positive X on the product side. And of course, E for equilibrium concentrations, we just add down the column. So this is X and that is X. All right, so our KB, of course, is our 1.7 times 10 to the negative ninth. And your equilibrium constant is always going to be products over reactants. So I'm just writing my products over the concentration of my reactants. There we go. And now I'm going to plug in each of these, and that really looks like a Y over there in these places. Let me fix that. That is actually an X. So now I've got 1.7 times 10 to the negative ninth is equal to X times X over 0.1 minus X. Now what we really want to do is we want to drop that minus X so we don't have to solve a more complex quadratic. We really just want that X squared in the numerator. And of course, to do that, we can run what I call the 500 rule. And then once we solve for X, we can check with the 5% rule. The other thing you can do is if you notice the KB for pyridine is 10 to the negative ninth. And that is a very, very small KB. So our approximation should be good. So if you're in a situation where you don't have time to check your approximations, I'd say generally if you're 10 to the negative fourth or smaller, you're going to be okay. Some people say 10 to the negative third. I kind of find those to be borderline depending on what your concentration is. But 10 to the negative ninth, you're going to see we're definitely going to be fine with our approximation. So I'm first going to do my 500 rule, which is my initial concentration of base over my KB should be greater than 500. So my initial concentration is again 0.1 molar. My KB is 1.7 times 10 to the negative ninth. Again, we want that to be greater than 500. And when I do this calculation, I get a very large number, times 10 to the seventh. So we're definitely greater than 500. We're like not even close. So even if you just ran the 500 rule, and you can see how much larger this is, then probably don't need to run the 5% rule. But anyway, what this means is we can drop that minus X. So we know that the 0.1 minus X is going to be approximately the same value as just 0.1. So we can drop that to 0. And now let's finish out our calculation. So now we've got 1.7 times 10 to the negative ninth. Now this simplifies to X squared over 0.1. So this is really simple to solve. So X equals 1.3 times 10 to the negative fifth. All right, so here is where students get confused or they just lose track of where they are. Remember, you solved for X, but what is X? So you need to go back to your ice table and figure out what X is. So X is our consumed or our change. In terms of concentration, it's how much protonated base we have and also how much hydroxide we have. So this is our concentration of hydroxide. And that's really important because, of course, ultimately we want pH. So there are two different ways that you can go about getting pH when you have your concentration of hydroxide. I like to first calculate pOH, subtract 14, and then get my pH. You can also take your concentration of hydroxide, use your KW, find your concentration of hydronium, and calculate your pH that way. Either way, you're going to get the same answer. But again, I like to take my concentration of hydroxide and calculate pOH. So pOH is equal to negative log concentration of hydroxide, which I know because I just calculated it. 1.3 times 10 to the negative fifth. So my POH is equal to 4.89. Again, remember this is POH. We want to get pH. So of course we just take 14 minus 4.89 and that gives us our pH, which is 9.11. So at this point, you should be doing a little bit of a logic check. Does this make sense to have a pH of 9.11? Well, yes, it does. I have a base in solution. This is where hopefully you can also catch a mistake if you've stopped at this point and you thought that that was pH instead of POH. It wouldn't make sense to have a pH that is acidic when you have a weak base in solution. So always do that quick logic check. Does this make sense? Yes, it makes sense. I've got a basic pH. That's exactly what I want. Okay, so that is part A. Let's go on to part B. All right, so in part B, we have added, I'll write this up here, we have added 15 milliliters of 0.1 molar nitric acid. Okay, so the first thing that we need to do is we need to do our stoichiometry. And then once we're done with our stoichiometry, then we can do our equilibrium side. This is what makes these problems really long, is because you're doing stoichiometry and then equilibrium very often, and definitely at this point. So we are still before the equivalence point, which means that we're going to have more base than acid. And I'll show you this when we do our stoichiometry. Okay, so stoichiometry first. All right, so to do our stoichiometry, of course, we need not concentration, we need moles. So I am going to get both my moles of my nitric acid, and I haven't yet calculated moles of my base, so I'm going to need both of those. Let's start with nitric acid because I've got the numbers right there. Okay, so remember when you have molarity as the capital M, that is the same thing as having moles of nitric acid over 1 liter of solution. And the reason why I write it like this is because to do your conversion factor, you can see that you've actually got a complex unit, which means you have a unit in the numerator and a unit in the denominator. You want to make sure that your units cancel so that, in this case, I want moles out. Okay, so I'm going to multiply this by 15 milliliters. But of course, milliliters doesn't cancel with liters, so you have to put in your conversion factor from milliliters to liters. Now, when you do this often, you end up just doing this in your head, which is totally fine. But I think it's always good to make sure that you can still do it step by step and that you're not flipping anything. Because here, remember, you've got to divide by 1,000. And I see a lot of students who accidentally multiply by 1,000. Okay, so this gives me 0.0015 moles of nitric acid. Great. I need to do the same thing and get my moles of pyridine. Obviously, this is going to be a similar calculation. I'm going to take my molarity, which is my same concentration. But remember, for your pyridine, so this is something to just check. I mean, I have to keep flipping back and forth. We started with a 25 milliliter sample of pyridine. So that is our volume of pyridine. Again, when you've got these titrations and you have multiple volumes kind of all over the place, make sure you're pairing that volume, not just with milliliters or liters, but with a particular molecule. Because again, that's another common mistake I see, is students will put the wrong volume with the wrong molecule just because they're not keeping track. And that's not something you want to do because, of course, that's going to lead you to the wrong answer. Okay, and not forgetting my conversion factor from milliliters to liters. So you can see I get my cancellation, and now I've got my moles of base, or my moles of pyridine, and this is 0.0025 moles of pyridine. Let's write out the chemical equation. This is a one-to-one chemical equation, but writing it out is going to help you see it a little bit easier. So we have nitric acid plus our pyridine gives us our protonated pyridine plus nitrate. Now notice I gave this a right-hand arrow only. That is because this is a stoichiometry problem. This is not an equilibrium. Once you have a strong acid, it's going to push that reaction forward and it is not going to go reverse. So this is true in our case where we have a strong acid and a weak base, but it's also true if you have a weak acid and a strong base. So as long as one of your reactants is strong, it's going to push the reaction to the right only, and you don't have to worry about equilibrium at this point. This is why I say that we're doing our stoichiometry first, because we are. This reaction only goes to the right. Okay, so here is our chemical equation. You can check and make sure, is this balanced? Yes, this is a balanced chemical equation, which means we have a 1-to-1 ratio, which makes our limiting reactant problem a lot easier, right? Because I know that I can just take the smallest one here, right? So my nitric acid is going to be my limiting reactant, and my base is going to be in excess. Now, what I find easier when I'm doing these problems, and I think it's just because I'm automatically thinking of ice tables, is I set up a table for my stoichiometry. So I think I have shown this before in a live stream, but I start here with my number of moles of my reactants that I have. So I just calculated these. 0.15 and 0.0025, and of course initially I have no product. Then how much am I going to use? Well, this is determined by my limiting reactant, which in this case is my nitric acid. So I'm using up all of my nitric acid. That's going to go to 0. This is not going to go to 0, and of course you are forming product. So you can see how it is similar to an ice table, although it is not in equilibrium. But you're using up reactant and you are forming product. Okay, and so then at the end of my stoichiometry, of course my limiting reactant has gone to 0 because I've used it all up. I have a little bit of base left, 0.001. And of course I have some product that is formed. And this is very important for your titration because now once we're done with our stoichiometry, we have to do our equilibrium. And it's really important to know how much of your weak acid or your conjugate acid of your base that you form. Now, we can simplify this. For our nitrate, we do have some nitrate that's formed. But remember, nitrate is the conjugate base of a strong acid, which means it's just a spectator ion. So I'll just write that as a note. Nitrate is a spectator ion. It has no acid or base properties, so we don't have to worry about it for our equilibrium problem. However, our protonated base is a weak acid. It does have acid-base properties. It's not a spectator ion, so we need to keep that in mind as we're getting ready to do our equilibrium problem. And for that, I am going to use an ice table, although you can also use Henderson-Hasselbalch. You just have to make sure that you use the base form of Henderson-Hasselbalch. But I'm going to show this with equilibrium just because why not? Let's just show it with equilibrium. Okay, so let's go on to our next blank page. So we've got, again, our base in aqueous solution. It's in equilibrium. We're going to get our protonated base and our hydroxide. So this is the same equilibrium reaction that we wrote for our part A, but of course our numbers are going to be different here. So we need to get concentration of our base and we need to get concentration of our protonated base. So remember, you made some moles of protonated base and we need to take that into account. But when you do your equilibrium table, you're working with concentrations. These are moles. So we need to first get our concentration. So I need to get my concentration of my base and I need to get my concentration of my protonated base. Now this is really easy because we just are going to use molarity here. So my concentration of my base is going to be my moles of base over my volume of solution. Now my volume of solution is my 25 milliliters that I started with. That's my sample. And how much acid have I added at this point? I've added 15 milliliters. So then my concentration becomes 0.001 moles of base over 40 milliliters or 0.04 liters of solution. Okay, so this gives me a concentration of base of 0.025. I'm going to do the same thing for my protonated base. I've formed 0.0015 moles of protonated base. Again, I'm over the same volume of solution because this is all presumably getting titrated in the same flask. And I get a concentration of 0.0375. Okay, so now that I've got my concentrations, I am ready to go back to my ice table. So let's get these concentrations in. 0.025. I am starting with a concentration of my protonated base, and of course I don't have any hydroxide yet. Sorry, this is I, so C becomes minus X, X, X. Again, you know that your equilibrium is going to shift to the right because right now you have no hydroxide. That is going to push the equilibrium to the right to form at least a little bit of hydroxide. And let's get our equilibrium concentrations. 0.25 minus X, 375. This is plus X, and of course our hydroxide is just X. I'm still going to do the same thing that I did with my first step. I'm going to get my Kb as just products over reactants. Products over reactants, and I have these concentrations right here. But of course, I'm going to want to simplify. Plus X times X over 0.025 minus X. Now, just to save time, we've already talked about how our Kb here is 1.7 times 10 to the negative ninth. It's very, very small. So I'm just going to go ahead and assume that these terms are essentially zero, and I can solve this equation. It's a linear equation. It's not even a quadratic because all I have is my X here. Let's see, this simplifies to 1.7 times 10 to the negative ninth. My numerator becomes this. There's my variable, and of course my denominator is now just a constant. You can solve for X, and you get times 10 to the negative ninth. Again, make sure you remember what X is. Go to your equilibrium or your ice table. X is our concentration of hydroxide, which means, again, I'm going to calculate POH first, and then I'm going to calculate pH. So this is negative log of 1.13 times 10 to the negative ninth. This gives me a POH of 8.94, which gives me a pH of 5.05. Okay, so again, we do our logic check. If we remember from part A, our pH started at 9.11. What have we added to the solution? We've added acid. So we do expect our pH to drop. So did our pH drop? Yes, our pH dropped quite a bit, right? So remember, we're adding a strong acid here. Okay, so again, that was when you added some acid, but not enough to reach the equivalence point. So let's go ahead and move on to part C. This is what's happening at our equivalence point. Okay, I am definitely going to need a couple more pages here. So, you know what? I'm just going to give myself 3. All right, so at the equivalence point, we have 25 milliliters of our nitric acid has been added. And we still have our 25 milliliters of base that we started with. So just like we did for part B, we've got to do our stoichiometry first, and then we'll handle any equilibrium that we need to deal with. So starting with our stoichiometry. I already know how many moles of base because I just calculated that, but I need to calculate my moles of acid because that has changed. I've added more acid. I've added a total of 25 milliliters. So here is my concentration over 1 liter of solution. Again, I've added 25 milliliters. Don't forget to convert milliliters to liters. Again, at some point, you'll just do that in your head, but that's fine. We don't have to do that right now. You can always, always write things out. And again, I have the same number of moles of base because I calculated that. Whoops, back one more. Right back here. So here's how many moles of base that we started with. That is going to be a constant throughout because you start with a certain volume of base and we're just adding more and more acid, but we're not adding more base at this point. Okay, equivalence point. Your moles of acid equal your moles of base. Yeah, I can't quite fit it. This is different from an end point. An end point is when you're in the lab and you're doing a titration and you're looking for usually a color change in your indicator. That is your end point. It is not exactly the same as your equivalence point. Equivalence point has to do with your stoichiometry. Endpoint has to do with your indicator and where that changes color. Now, this is why you choose your indicator very carefully because you want your indicator to change color as close to the equivalence point as you can possibly make it, but they are not the same thing. That's another classic question again on the AP exam, or I see it often pop up in Gen Chem 1 college classes too. Difference between equivalence and endpoint. Okay, so we're still doing our stoichiometry. Let's write our balanced chemical equation for our acid plus our base. Remember, this is a forward reaction only. So I only have my right-hand arrow here. I'm still going to use my table. So I have the same number of moles of each, 2, 5. And of course, initially I don't have any product. How much am I going to use? I'm using up my limiting reactant, which in this case is both my acid and my base because they are the same. Sorry, these are decimals in here. Those are not coming out. And of course, I am forming product. All right, so how much do I have at the end of my stoichiometry? I don't have any more nitric acid. I have no more base, but I do have some protonated base. And I do have some nitrate. But remember, like we discussed last time, nitrate is just a spectator ion. I really don't care about that. For my equilibrium, I care about my protonated base because that is a weak acid in solution. It is in equilibrium, and I need to take that into account to calculate the pH. Okay, so this is my stoichiometry. Remember, these are moles. But to do my equilibrium, I'm going to need concentration. So I'm going to need concentration of my protonated base. Okay, I know how many moles I have. 0.0025 moles. What is my volume at this point? Again, I started with 25 milliliters for my sample of base. How much acid have I added at this point? I've added 25 milliliters. Okay, so this is going to be my number of moles over 50 milliliters or 0.050 liters. And this gives me a concentration of 0.05 molar. Okay, at this point, I am ready to go ahead and set up my ice table. I'm going to do this on the next page. So remember, you have your protonated base in aqueous solution. It is a weak acid. You're going to form some base and some hydronium. Okay, so ice, initial concentration, 0.05. I don't have any of this. That looks like an X. That is a plus. I'm writing too fast and too sloppily. Okay, consumed. I'm going to form some product. And equilibrium. This. I know sometimes you feel like you keep doing the same equations over and over again, right? Okay. Notice I call this a Ka because remember your protonated base is the conjugate acid of your base. It is a weak acid. And now I need to plug in here. So this is X times X over 0.05 minus X. And you might be wondering at this point, We don't have Ka. We've got a Kb, but we don't have a Ka. And they're like, yes, you're exactly right. We don't have a Ka, but we can get a Ka. So remember, when you have an acid-base conjugate pair, their equilibrium constants are related by Kw. So Kw equals Ka times Kb for a conjugate pair. We know the Kb, we always know Kw, so we can calculate the Ka. So Kw is 1 times 10 to the negative 14th. We're going to calculate our Ka, and our Kb is 1.7 times 10 to the negative 9th. All right, so our Ka, where is that calculation? Here it is 5.88 times 10 to the negative 6. So we're still plenty small enough to assume that our minus x doesn't make any difference with our 0.05 molar. So I'm going to drop that term, and that's just going to make solving this quadratic so much easier. Okay, so we have 5.88 times 10 to the negative 6 equals x squared over 0.05. So when I solve for x, I get 5.42 times 10 to the negative 4th. Now again, as always, remember, what does x equal? X equals my hydronium concentration, which means calculating pH is a lot more straightforward. I'm not calculating pOH first. I'm just going straight to pH. Okay, hydronium concentration. So I have negative log of 5.42 times 10 to the negative 4th to get my pH. And I get a pH of 3.27. Does this make sense, right? So we always do our logic check here. Does this make sense to have an acidic pH at the equivalence point? Well, yes, it does, because we have a weak acid in solution, right? We've got our protonated base. So yeah, our pH ought to be less than 7. It shouldn't be hugely less than 7. We shouldn't have a pH of, 0.5 or 1, but we do have a fairly acidic solution. So that is our pH at the equivalence point. So remember, if you have a strong acid, a strong base, your pH is going to equal 7. But once you have one of those is weak, your pH is not going to end up at 7. Okay. That is part C. We've got one more part to do. Okay, good. I still have one more blank page. I gave myself enough. So we have part D, and this is when 35 milliliters of nitric acid has been added. So this is after the equivalence point. So at this point, we've got excess acid, which makes our stoichiometry really easy, right? Okay, so let's figure out stoichiometry. Let's figure out how many moles of acid we've added at this point. So again, starting with my concentration over 1 liter of solution. So at this point, I have added 35 milliliters. And again, knowing that you've passed the equivalence point already lets you know what the limiting reagent is here, right? So my base is going to be my limiting reagent, and my acid is going to be in excess. That's just nice to know ahead of time, so that as you're doing your stoichiometry, because your stoichiometry is a limiting reagent problem, you already know which one is limiting and which one is in excess. And so you're not thinking, wait, did I choose the right limiting reagent? No, you already know the limiting reagent. Okay, and we still had our same number of moles of base that we started with. Sorry, this is a 3. That looked a little janky. Okay, so let's get our equation up here for our acid reacting with our base that we have seen before. Remember, this is right-hand arrow only. We're doing stoichiometry here. We're not doing equilibrium. So start. I'm starting with 0.0035 moles of nitric acid. I have 0.0025 moles of base. Those are both 0. How much is used? That's dependent on my limiting reactant, which I know in this case is my base. So I'm going to use up however many moles of base I have, which is, of course, 0.0025. And I'm going to make a little bit of protonated base, and I'm going to make a little bit of nitrate. Okay, so at the end of my stoichiometry, I have 0.001 moles of nitric acid. I don't have any base left. I have a little bit of my weak acid, my protonated base, and of course I have a little bit of nitrate, which I don't care about because it doesn't do anything in terms of my acid-base properties or in terms of my pH. Now, at this point, we've actually got a really easy problem because we have moles of a strong acid, which means our smaller number of moles of our weak acid just are not going to make a difference in terms of our pH. We only need to focus on our moles of our nitric acid. So this makes pH really easy to calculate because, of course, at this point, if we've got a strong acid, our pH is just negative log concentration of our nitric acid, right? So this is the same thing as saying negative log of hydronium because our strong acid here is a monoprotic acid, which means the concentration of the acid is the concentration of hydronium. So really our last, I would say, difficult or tricky step is to remember that you have calculated moles here. And we need to get concentration to plug into our pH. So I need to get a concentration of nitric acid. All right, I know how many moles I have because I just calculated that with my stoichiometry. What is my total volume? I started with a 25 milliliter sample. I have added now 35 milliliters. So my concentration is over 60 liters, or sorry, 60 milliliters, 0.06 liters. So my concentration of my nitric acid is 0.017. Of course, this is the same as the concentration of my hydronium. So my pH for my final step is just negative log of 0.017. And so my pH is 1.78. Again, does this make sense? Yes, this makes sense because we've got a strong acid in solution now. All right, so we've neutralized all our base. That's totally gone. And now we've got a strong acid in solution. You'll notice our pH has dropped even more. So this is a titration problem starting with a weak base, continuously adding strong acid until our base is fully titrated and then beyond. So I hope you guys found this helpful. Again, it's a little twist of kind of a classic problem of usually you have a weak acid titrated with a strong base. But again, these little twists are something that you see pop up very often in exams. As always, let me know what you're working with in class, what you would like to see on the live streams. I'm happy to do that, and I hope to see you guys next week. Thanks so much. Bye.